Hi everyone. Thank you to the organizers for inviting me. This is my first SAND and pretty excited to present our work. This is work with Alex on modeling neural activity with conditionally linear dynamical systems. It's great to go after Adam. It sets this tone for approximating nonlinear system with linear approximations. And yeah, I'll just go right in. I want to start by acknowledging our collaborators on this work. Amin, just from day one, has been a great collaborator. We started everything together. David and Jonathan provided a lot of feedback. Jonathan is the voice in the back that Ben so aptly described. And Alex has been the voice in the front, really giving us, oversteering this whole project. And it all started from Cosine 2024, where Alex talked about approximating linear systems with time-varying linear systems, and it seemed hard but fun. So this is it, basically. A motivation for this work is that a cornerstone of basically neural dynamics research that we've been investigating is that they're affected by external covariates. And our goal is to understand how those external covariates affect the neural dynamics. And by external covariates, I really mean anything external that we have access to as experimenters. They can be sensory stimuli, task variables, behavior. Here I've been showing you a video of a target pursuit task from the Hayden lab, and this describes well the typical experimental setting that we're considering, where we have an animal performing a certain task, we have access to many aspects of the task, and we do neural recordings at the same time. This is the setting that we're considering here. And in our approach of understanding how neural dynamics are affected by these external covariates, linear dynamical systems have been super influential. They're very interpretable and easy to fit, and this goes back decades of work. And we can think back about Adam's slide from memming, describing this whole progression from LDS models all the way to more complex models. Because indeed, linear dynamical systems have the shortcomings that most systems are nonlinear, the systems that we consider. And so there's been this proliferation of nonlinear methods to address these systems. They've been increasingly accurate, but also increasingly complex. And our goal is to find an in-between for these things. And we've noticed that the influence of experimental conditions on dynamics remains relatively understudied in comparison to the focus on increasingly strong unsupervised methods. Unsupervised methods, almost by definition, don't necessarily rely on the conditions. But we saw here a possibility for a correlation structure between experimental conditions and neural dynamics that was perhaps underutilized. And so we asked, can we leverage this correlation structure to bridge the benefits of linear and nonlinear methods? And so the outline for this talk is I'm going to introduce the conditionally linear dynamical system class of models. And the takeaways I'd like you to walk away with, and my goal will be to convince you of them, is that CLDS models are both locally interpretable while being expressive, which can be a hard balance to strike. And they're pretty easy to fit and adapt to your specific tasks. And so the outline for this talk, I'll start with the model and inference before moving to an experiment, a synthetic experiment that is nonlinear in nature, but we approximate it with this method before two example data sets. All right, so going into it, the setting that we're considering here is that we have access to neural recordings Y, using the same notation as we've seen, and conditions UT. Importantly, so both of these things are known to us, and the conditions, for instance, in this target pursuit task could be the specific context that you're considering, the target on the screen, the joystick movements, anything that correlates with the neural activity Y. These conditions can be time varying or constant within trial, like a context. They can be discrete or continuous. What matters is that you know them. And so a typical approach is to consider a linear dynamical system like what we have here, where xt plus 1 is linear dynamics in X, with a linear encoding for for U, with some epsilon noise, and from which we get observations Y that are also linearly decoded from the xt, with again, linear encoding perturbations du. And here I'm considering continuous valued neural activity, think like smoothed firing rates, not Poisson spikes. And our approach is to rethink of these coefficients of the linear dynamics as being nonlinear functions of external conditions. So we've replaced A, B, C, and D with functions of U. And this nonlinear dependency on the conditions is captured by introducing a GP prior over A, B, C, and D. So now every ijth entry of all these parameters is a full function over conditions. We parameterize and put it prior over these functions with a weight space characterization of GPs, where the ijth entry is now a weighted sum with weights W. Sorry, is there reverb? Okay. With the weights W that are sampled from a normal Gaussian and that weigh those basis functions phi that we have here. These basis functions are a sort of a degree of freedom. We've chosen them so that we approximate basically a standard squared exponential kernel form. And the source of randomness in A purely comes from the weights W, and that will be important later. And so this is the sort of graphical representation of the type of models that we're considering, where we have a linear dynamics in X, and where the conditions U at every time step t influence what are the linear dynamics in X and what is the decoding X to Y, with Y being the neural data that we observe. And sort of a key insight here is that this makes for a system that is nonlinear over conditions, but linear in time and in dynamics. So here is our hope to leverage these two things, leverage the linearity over dynamics, which we know how to handle, and the nonlinearity over conditions for expressivity. And so from estimates of the coefficients A, B, C, and D, given known values for them, they are now functions of U, and for any known sequence of conditions U, it's an LDS model. So we have exact latent state inference with Kalman smoothing, marginal log likelihood calculations, filtering for the latent states, all these beautiful things that we know how to do in closed form and exactly with LDS models. We benefit from them. But now the question is, how do I get those estimates of the parameters? How do we perform parameter inference for A, B, C, and D, or specifically the weights of them? And for that, we can leverage the Gaussian linearity aspects of our formulation. So let's focus on one component of this, and I'm glad that we're here at Sen. I get to actually go into the details of the inference. Let's focus on this problem here, where xt plus 1 is AUT, this function that we want to estimate, xt plus epsilon, where A is in the parameterization I showed you before. Our problem is to infer W given everything else, given also X for now. And the trick is to realize that this can be cast as a linear regression in just another space. And using ideas of linear regression to perform updates is sort of typical in an LDS, and that was a key theme throughout this work, was to understand what we can leverage from known methods in LDS models and port them to a more nonlinear or complex method. So how can we perform inference in this setting? Realize that what we have on the left-hand side that we've just seen can be written as the right-hand side here, where I've put all the weights W into this big matrix, capital W here, and our basis functions that we know, our U's that we know, and our X can all be put together into this Kronecker expanded form. This whole thing that I'll call Z is known to us. So see how we have X that we know, Z that we know, we want to estimate W, and it's just plus epsilon Gaussian noise. This is your typical linear regression setting with a prior over W. We know how to solve this exactly. This is the solution for W in this setting. And now the idea is just, okay, let's repeat this for all the parameters over and over again. We can put that into an expectation maximization algorithm where in our E step, we get estimates of X. We get estimates of all the latents. We do this E step using standard LDS methods that we can do exactly in closed form. And then for the M step, we do what we have here at the above, which is also, again, in closed form. And all of this gives us still the guarantees of EM. We have monotonic ascent guarantees on the marginal log-like, and actually the log posterior objective for these. Great. So this is how we do inference. I've told you how we do it. Now I'll show you what we can do with it. Our first experiment was to consider a nonlinear system. It's already been mentioned this morning, the idea of ring attractors. We decided to focus on the ring attractor, specifically within the context of head direction. We know it's a fundamental and well-studied model within this field, of thinking of this ring attractor as capturing the head direction of a mouse within, say, the head direction system. Looking at this nonlinear system that is inherently nonlinear, you can't write this as a linear model. Our insight, or at least our perspective to devise this synthetic experiment, was to realize that we can decompose this nonlinear system into smoothly varying linear systems. For every head direction theta, I have linear line attractor dynamics about the tangent of the ring. So we see it as linear dynamics on the right here and all around the circle. For every head direction, it's linear, but together, when we compose over all conditions, it makes for a nonlinear system. And for the synthetic experiment, we read off neural activity Y from it. And this is a CLDS model by definition. It's linear per conditions. And so here at the bottom, our goal in this setting was to infer the flow fields as a function of theta, which we perform here in C and D. You see the dynamics A and the bias B as a function of theta. This is the inferred function fully. I can use that for any theta I want. And you see in black is the true and in orange is the recovered. And if you can't see too well the black, is because we hopefully did a good job, the two align. And in E is the co-smoothing reconstruction, another method that we consider for just reconstruction of the dynamics. So this was our quality test to just see if we can perform inference well enough. And then now we move to how can we deploy these things to real data? And so a key aspect of this is we have to think what are the behavioral covariates? What are the neural covariates that we have, like context, stimuli, understanding which one to choose and how they affect the neural dynamics. So we'll be looking at two examples for this. The first one is mouse head direction, building off on our example that we just saw. So we considered mice head direction thalamic recordings in an open environment that was collected by Adrian Perrache back in the Buzaki lab. And the specific CLDS instance that we consider in this work is to think of the head direction as the condition. UT is theta t. There's recorded head direction at any given time during a trial. And we parameterize A, B, and C with this without a D for the two experiments to come. And what we see is first that there's a good fit. We can reconstruct single neurons, as this is more of a quality check. But on the right, we see that the model captures well the empirical tuning curves. If we can write down what the tuning curve is in this model, it's this C with the expected X. And the red, the model matches the blue quite well. This is a quality of fit. And now in looking a bit deeper into what is learned by the model, this is essentially a noisier version of this synthetic head direction attractor that we conceived. Here I'm plotting how the dynamics vary as a function of head direction, that color map here. And in black is the fixed points for the system. Solving for fixed points can be quite a tedious task sometimes, but here, given that it's a linear dynamical system, I can obtain a form for the fixed points, enclosed form, as a function of theta for any theta. So this is this black line that you see, and we have the attracting dynamics, fixed point dynamics for every point on that line. It's not a tangent, it's not a line attractor as it was in our synthetic example, it's now a purely attractive fixed point. But we do see these head direction fixed points appearing in the data. Next, we sought to look at a more standard task, often considered in the field of motor center outreaching task in macaques. So we looked at a quite well-known data set obtained from the Chinoy lab of PMD recordings. And in this case, it's less about the insights and the data. It's more about how you can adapt the CLDS to the specific setting. We use the trial angle, the cued angle that was q to the monkey, and a time-dependent reach variable zt that went from 0 to 1 during the reach. This sort of variable is what you would want to infer in, say, in an unsupervised method that has discrete latent states. Here, that's not our goal. Our goal is to use what we know the behavioral correlates and see how they relate with the neural activity. So we parameterized with those two variables as our conditions, and we use this form here at the bottom of CLDS with a fixed decoding matrix C, in this case. And basically, we found, again, fixed point dynamics, now during both the delay and the reach period. I can, again, solve for the fixed points using the equation I showed before, and we saw two rings of attracting fixed points. And which is relatively expected. What was interesting is to now see, given that the CLDS, and I'll conclude on this, the CLDS model uses a GP prior over conditions. So this is a way to regularize. It's a way to pull statistical information from nearby conditions. Given one condition, I can use nearby ones to inform what my parameters should be. So we sought to see, okay, how well can we do in data-limited regimes? If instead of using the whole data set, I consider a certain number of conditions, of trials for each condition. And here, what I mean by conditions is the reach angle. And so here we see the R squared as a function of the number of training trials used per condition, going as little as one trial for every reach angle to the whole data set. And with this specific co-smoothing score, we saw that our CLDS was able to perform well even compared to standard models in the field that range from more nonlinear methods, linear, or more classically unsupervised methods. So with that, I'd like to conclude and leave you on this very wordy slide where we described conditionally linear dynamical systems, a framework that hopefully bridges both linear classical methods and contemporary, more flexible nonlinear approaches. And I hope to show you a little bit our results, how they're locally interpretable and easy to fit, leveraging aspects of linearity. But they're also expressive using, this time, the nonlinearity in the parameters. And because this nonlinearity is captured through GP priors, they're also very data efficient since they can pull statistical power across nearby conditions. So yeah, I'll open it for questions, and you have an archive here and a GitHub link to start working with this. Thank you.
Okay, time for one, maybe two questions.
Yes.
Just confirming, so during inference, you need
Yeah, doing everything. And we really assume them to be observed, which is a big departure from, say, unsupervised methods.
Up to you, Victor.
Oh, no, decisions, no, I hate it. Okay, I'll find you afterwards.
Uncertainty quantification in these models and whether you would expect them to like recapitulate single trial variability, that kind of thing. I don't know if you've looked into that at all.
So for single trial variability, indeed, like we can, with an LDS, we can say for marginalize over latents, get some sort of full distributions over observations. And this we can use standard methods in LDS models, again, conditioned on the parameter sequence, which I hope gets to your point. Another point that I don't know if it addresses necessarily is the posterior and the parameters themselves. Indeed, we've been using a GP prior to get map estimates, point estimates of the parameters. Work could be done to extend this to have a full posterior over parameters as well. They're using the GPs or sampling methods that could leverage the fact that the marginal log-like can be estimated point-wise exactly. So I hope that gets to it.